Thank you, Dr. DeBoer. Okay, and welcome. Glad you're out this evening for a special science seminar. And you've got a treat in store. I'm going to tell just a few things on Dr. Bijan Nemati before he comes up and tells you all about detecting exoplanets. We met each other, I think, for the first time in 1991, which is a while ago. A ways back in a place called Ithaca, New York. We were both postdocs at that time. Now, Dr. Nemati had already come. He grew up in Iran. I don't know if he's going to talk all about his life story tonight, so I'll talk a little bit about it. And he grew up in Iran, and he came out of Iran about the time, I guess, the Shah did. And so, as a 17-year-old, he's over here in the States. And he ends up going to the University of Colorado, where he does his physics degree at the University of Colorado. And then he went out to do his PhD at the University of Washington in Seattle. And by the time I met him, he was already a postdoc for, was it Oklahoma University? Or
State University of New York.
State University of New York. You weren't yet at Oklahoma. Okay. Well, we were both postdocs, and that's a lowly thing to be. It's a very humbling life as a postdoc. And we didn't know what we were going to do with our careers because we knew at that time that the big project in particle physics here in the United States was going to be the super collider, and it was going to be built here near Waxahachie, Texas. Well, that project got started, but then it got killed midway through. I think they got a quarter of the tunnel dug, but they killed that project. And so a lot of us were really wondering what to do with our lives. And this relates to my relationship with Dr. Nemati because he was one of two other Christians that were working there at Wilson's synchrotron laboratory at that time in the early 90s. And we started, at Dr. Nemati's suggestion, I don't think he remembers, but I do. But he suggested we start meeting together for prayer time once a week. And so we did. And I tell you, that was very helpful for me because I didn't know really what I was going to do with my life. And that prayer time just helped me to focus on the Lord and what the Lord would have me do. And that was really good because there were three of us that were meeting regularly, and we all ended up going in different directions in life after that. He stayed on the cutting edge of physics, and I guess he'll show you a little bit about the things that he's done in his life. And I felt led to go into some sort of Christian ministry of some kind. But the Lord was going to use my background in physics. And the other one went into physics education research, and he's a professor at the University of Wisconsin, Oshkosh. So the Lord was taking us different directions at that time, but we all needed that prayer time. And that was a time that was just instrumental, I think, in all of our lives, of really helping us focus on God and focus on seeking Him more than anything else, not worrying about my future. What am I going to do? What I'm going to eat? Or what am I going to do for a living? You know, don't worry about those things. God does not want you to worry about those things. He wants you to seek Him. That's what He wants. And I appreciate this because he has a heart for God. And he was somebody I really look up to as somebody who has been seeking God his whole life, serving God his whole life. And everything that he's done has been a direct outcome of his Christian commitment. And so I really appreciate this guy. I don't know, I guess I'm not going to tell any embarrassing stories about him because these guys have come out to hear about exoplanets. So I'm going to go ahead and turn this over to Dr. Nemati. Give him a welcome, please.
Thank you. I just remember, it's not even a joke. I think the director of Fermilab said when he was graduating, this was some years ago, that former director said, the economy looked so bad that they were telling each other, well, when I graduate, I'm going to be unemployed in physics. What are you going to be unemployed in? So we start here on that note with the subject of exoplanets, extrasolar planets. So planets, we know what planets are. The planets originally that word came from wandering stars, which we then found out to be objects that are really close to us relative to the other things we see in the sky. And it was not known for a very long time, though suspected, that planets should be abundant in the universe around other stars, but it was not known until the mid-90s that that was in fact the case. There was one or two claims for observation of planets around other stars proved to be wrong until in the mid-90s, where the first one was discovered, which is probably around where you guys were born. And just before that, hardly anybody believed, there was no evidence. The interest in exoplanets is huge. It shows that when there's a discovery, it shows up in the front page of newspapers and magazines and websites. And the big questions with planets in general, and particularly exoplanets, because we know and appreciate our solar system, of course. And in fact, there's a lot to appreciate about our solar system, and there's a lot to talk about there. But today, what we want to do is take a step back and think more generically at planets. So here's our solar system. There's the sun. This is obviously not to scale. At about 1 astronomical unit, this 150 million kilometers is 1 astronomical unit, which is the distance between us and the sun. At 1 AU is us. At 2 AU is Mars. 5 AU is Jupiter. Then there's Saturn and Neptune and I think I missed Uranus in there. But the attributes of the planets that we are interested in are, and the questions that we're interested in, is what is, for example, the processes that cause the formation of planets? And what makes a Saturn versus a Mars or a Mercury? So what are the planetary formation processes that are important? And is the solar system common? Because obviously our solar system is very, accommodates us, for sure. It turns out that the conditions for accommodating our lives are many and very fine-tuned. And so it's a remarkable thing that we are in the just right solar system. But maybe the just right solar system is statistically possible to create a lot. Is that true? Is this borne out by observation? What makes for a habitable planet? That's a very big topic, which is a subject of some other talk. I'm not going to talk about that much tonight, maybe just touch on it a tiny bit, because you will find that in the titles. Earth 2.0 found, or a new habitable planet around, HR, blah, 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 blah. And so we would like to kind of have just a little bit of an introduction for what makes for a habitable planet. And then the final thing is, can we detect the habitability of a distant planet, a planet around another star? And that comes to the subject that has really sort of become my field now, and I'll tell you guys a story about that later. So I mentioned that the first discovery of an exoplanet was in '95. There was a twin discovery. There was a European discovery and an American discovery. This video is from the European Southern Observatory, but the discovery I'm going to show after that is the American one. So the discovery, whoops, that didn't work. I wasn't going to show you that. The discovery was centered on, I hope it starts. It would be a shame if we can't get that to work. So, is the video working on, sorry, is there a Wi-Fi working on this machine?
That should be hardwired in.
No, it's very strange. Alrighty. No, that wasn't it. I'm going to go out and try this once like this. Let's see if we can. Cannot play media. Now, why is that? Well, sorry, guys. Some cool videos are going to be lost, but I can't figure that out right away. Let's do this. John, get my laptop going, and we'll intercept this video later. Just put it up here, and we'll do without it. That's okay. That's okay. Sorry about that. I'm going to try one more time, but I'm not sure why this is happening. So anyway, what the video would have shown, which I will now animate for you, is basically the principle of operation of the thing that they used for this discovery was the principle that when a planet, when anything is interacting with anything else gravitationally, there is, by Newton's third, I think, law, there's for every action there's an equal and opposite reaction. So in an orbiting situation, the planet puts a force on the star puts a force on the planet. The force of the star on the planet is quite easy to discern because that follows essentially the orbiting thing. But what we don't pay attention to is that the star is actually orbiting the center of mass of the planet and star system also. So the star, if you look very carefully, like if you looked at our sun from, let's say, 10 parsecs away, if this is the size of the sun, which is about my fist for the moment, it wobbles around by about its diameter in response to the tug from the biggest, heaviest planet around, which is Jupiter, around it. The wobble, there's a perturbation to that wobble from the Earth, but it's like, I don't know, 1,000 times smaller, so it's very hard to discern that one. So so an observer that wants to look for planets around our system would not be able to see very easily Jupiter. Why? Because the light from Jupiter is reflected off the light from the sun. Now at night you can go out and see Jupiter. It's kind of bright. But compare how bright it is to when you try to go and don't try this, and look at the sun. It is about a factor of 1 billion difference in brightness. Okay, so it's hard enough to see the sun or the star. To see the planet is very hard. There's a second problem that I'll allude to later. But what you can do is see the indirect effect of the planet orbiting the sun. And that indirect effect is the wobble can have a signature in the spectrum of the star that you're looking at. So you can look at the spectrum of the star and then measure it periodically over. So I've got my laptop actually going, and I need help from perhaps Dr. DeBoer. Sorry to put you on the spot, sir, but that's great. So what we like to do is basically just connect this thing to that, and we'll just switch over if possible. So
you want to connect
the laptop to the projector.
Okay.
Is that possible?
Yeah.
Okay, that'd be great.
Because
Sorry.
you could have both this and your laptop.
Oh, okay.
You can put your laptop on the two TVs.
All right, let's do
You
that.
want that?
That would
All
be
right.
cool. Then we can go with that. If we can have audio on it too, that'd be
Yep.
great. And my apologies, everybody, but it'll be worth it. Okay, cool. This is ready to go. When that thing is going, we'll see. Perfect. Okay, very good. So this is 51 Pegasi, and what we are looking at is as you're looking at the star will be coming towards you at times and away from you because you're looking at this star and the star is wobbling. Now you can have an instrument that basically is looking for the spectrum from the star. Now the spectra of the stars can have a signature. You can look for one spectral line, and when the star is coming towards you, it will blue shift the light. Now, blue shift and red shift are essentially Doppler shift, and you experience Doppler shift when you're standing by the side of the highway and you hear, the pitch is high coming towards you from a car that's coming by, and then goes down. That's the blue shift, and then the red shift as it goes away from you. And so that will cause an oscillation as the star is going round and round, and you're down here looking, you'll see it red and blue shift, and these guys in 95 were able to get this beautiful curve of the spectrum of the star shifting in this nice, beautiful oscillatory way. That was a signature of the planet. From the amplitude of this, they could see things, say how massive it was. From the period of this, they could say something about how far away it was, and something about the masses as well. Oh, great, thanks. So we will see if after all the effort, this will now work, at least on this one. Sorry, it is going to work. Yeah. You see it? Yeah. So there it is. And so you can see that, you can see the spectrum is kind of shifting as it goes away and as it comes towards us. And that is the indirect method. Now, the important thing to realize is the planet is not directly observed. All we're inferring is we're just seeing the spectrum of the star go back and forth and become red and blue shifted, and we're inferring the planet from that. And we'll leave that guy alone, and we'll just move on. And so that was called the radial velocity technique. And with that, hundreds of exoplanets were discovered from the mid-90s onward. And when that was first done, the generic reaction was, okay, now there's lots of exoplanets we see, we're not special. But in fact, when you look at it more carefully, look at the data, what you see is, here's an interesting plot. This is a plot of the eccentricity of the planet orbit. What's eccentricity? Well, an orbit can be a circle, or it can be an ellipse. And the more elliptical it is, the more eccentric it is. So the eccentricity, by the time eccentricity is 0, you've got a perfect circle. When eccentricity is 1, it's like a line, going like that. So the thing that we have in our solar system is that Jupiter, and by the way, the sensitivity of the radial velocity technique at that time, and a little bit also now, though the sensitivity is much improved, was to very massive planets. The lighter planets, the radial velocity technique did not detect. But so most of these are like Jupiter-class planets, and here is a plot of, for many of these hundreds of extrasolar planets around other stars, what is the planet eccentricity distribution, and what is the period of the planet. Now, what Jupiter does for us is very interesting. Jupiter is in a low eccentricity outer orbit, and because of its very high mass, it sucks all the stuff around it to itself, so that comets and asteroids and other things basically it's just like a vacuum cleaner just kind of sweeping everything up for us. So it's very conveniently and politely in a low eccentricity outer orbit, which we like, we appreciate. But if we were around in one of these other systems, you see, many of these are very high eccentricity orbits, so that they come in and intrude on each other's orbital area, trajectory, and occasionally will bump a planet right off the solar system. But by the time you find the big population of low eccentricity, you are in these hot Jupiter mode, where the planet is whipping around the sun, at very, very tight radius. And when it does that, it causes instabilities in the orbits of the other planets. So this was something very interesting that we basically learned that what we had was fairly special compared to what we were observing. Many techniques have now been introduced since that time for detecting planets. What I was mentioning was radial velocity. And the telescope is looking at the star and sees the red and blue shift, doesn't see the planet. There's another technique called transit, where what you're doing is you're looking at the star and you wait till accidentally a planet will go by. Now, why do I say accidentally? Meaning that if you look at any given star, saying this is the star, the planet orbit, for all you know, might be like this. And you're looking at it from where you're sitting. You will never see that planet transiting because the orbit is that way. The orbit has to be this way for it to come in between you and your line of sight. If you think about it from a geometry standpoint, you'll find that that technique has a bias, because the farther away the planet is, the likelihood that it will be lined up with you is lower and lower. So the technique is kind of blind to planets that are far away. Just the ones nearby you can catch. And you have to be looking at a lot of planet stars to be able to find these accidental transits. A mission was devised to do this, called the Kepler mission, that has seen the largest number of exoplanets, but they're all around stars very far away, and because any nearby star, the probability is too low. Another technique uses Einstein's general relativistic process of bending of space and time to produce an effect called microlensing, where the joke is you see essentially a signal from a planet you can't see around the star you can't see. So it's a little bit tricky to get this one to actually work, but it actually will become a very important technique. Transits and microlensing are both kind of statistical. Their values are in statistics. You can look at gazillion situations and be able to count what fraction of the time you see what, and that's very valuable. But if you want to look at a star and you want to nail it, then does it have planets, does it not have planets, you have a couple of choices. One is called astrometry, where you basically measure the angle between that star and other stars, which I didn't have room for my 4, so I don't think I have astrometry there anymore. But instead, you have this other technique called direct imaging, where you just take a photo of what you've got and see if you see any planets. That's the thing that I'm now working on, and I'll explain what are the positives and what are the challenges of that technique. This just shows the wobble that we already were talking about. The mission that I was mentioning, Kepler, named after Johannes Kepler, famous Christian astronomer, one of the greatest astronomers of all time. So the Kepler mission basically took one patch of the sky, and that little pattern you see is what the sensor array in the back of this was looking like. So each one of those sensors was tied to a bit of real estate on the sky. So the Kepler mission just always stared at the same spot, just waiting and waiting to see a transit. And when a transit occurs, these are measurements. It's called photometry, for measuring light. So you're measuring the amount of light coming from the star, and suddenly it gets dimmed. By how much? Well, it goes relatively from 1.0 to 0.9998. So it's like maybe a few parts per million, 60 parts per million was the resolution of this. So what Kepler had was extremely good precision photometry, so that it could be sensitive to these dips. And it's amazing over the past few years how much we could actually learn from the length of the dip, from the depth of the dip, from details of the dip that this early picture doesn't show. So you can infer an awful lot about the exoplanets. So one of the fruits of Kepler mission has been the understanding now that only a few percent of sunlight stars have Earth-sized planets in their habitable zone. Now, I just used a phrase called habitable zone. What do I mean by habitable zone? Basically, it has to do with the notion of habitability, and there's a lot that goes into what makes a planet habitable. But as a minimum, everybody agrees that a planet that is habitable has to have liquid water somewhere on it. That liquid water is very important because of the unique characteristics of water, which we could go into at some length, but we won't. But basically, if you now say that I want liquid water around the star, you can ask the question, how far away should the planet be to get liquid water? If it's too close, the water boils off. If it's too far, all the water freezes over. So at some radius, that is the habitable zone, there is liquid water. Now, if the star is hot, it would not be hard to imagine that the habitable zone is going to be farther out. If the star is cold, it's going to be closer. And so this is a classic plot. This is a very old one, 1993, but because it's such a classic, I like using it, by Jim Casting, who is sort of iconic in this field. And he's showing the habitable zone as a function of distance from the star in AU units. Remember, 1 AU is the distance the Earth is from the sun. And on this plot, in a logarithmic scale, is the mass of the star divided by mass of our sun. So if you look here at the mass at 1, that means the ratio is 1, which means the mass of this sun-like star. That's our solar system. And you can see that the habitable zone, the range where below it you can't get liquid water, and above it you can't get liquid water. Below it you get runaway greenhouse. Too far away you get runaway glaciation. Think about this a little bit. Water is the most effective greenhouse gas. Actually, 99.5% of greenhouse effect is water. Now, if we get too close to the sun, the temperature goes up. The temperature causes the more water to go into the atmosphere, which causes more greenhouse effect. And it's a runaway greenhouse. And everything is super hot. If you go the other direction, it snows down and it's all white on the ground, which kind of makes it colder. I mean, it means the more of the light gets reflected back out to space, the planet gets colder, runaway glaciation. So there's a middle ground, and newer pictures of this, by the way, show the habitable zone is to be very narrow. I mean, it's like 1% closer, and we're a runaway greenhouse. But be that as it may, notionally this is still true, that there is a habitable zone, and Earth is the only one that's really in the habitable zone. That's us. So there's Mercury, Venus, Earth, Mars, and you can see Mars is just outside the habitable zone as a planet. There's another thing that's worth looking at here, and this is interesting, which is the tidal lock radius. That says that for what happens is that if you get too close to the object you're orbiting, your spin starts getting synchronized with your orbital angular speed. So that, you know, if you look at the moon, do you realize that you always see the same side of the moon? That's tidal locking. The moon's spin has been synchronized with its orbit. It's not that it's not spinning, it's just spinning exactly once around just as it goes once around, so that we always see the same side of the moon all the time. That's called tidal locking. Now the problem with tidal locking is that one side of the planet, you know, as you get closer to this, to the sun, to the star, than this line, one side of the star is always getting the sunlight, the other side is always getting the darkness. One side gets super hot and all the water boils off, the other side is snowing. And so the planet gets desiccated and is not there. So at the terminus, where the shadow, where there's like the evening morning terminus of the planet, there is some liquid water. There is also some newer theories that say that convective processes may make it better. So it's possible that we'll find out that they're not quite as bad, but they're definitely not your favorite, you know, to have the. Okay, now the trick for me is always press the right space bar, not the left. Okay, so here's another one of the Kepler discoveries. This is a very interesting plot on a logarithmic radial scale showing planets that we have discovered around other stars. The blue ones are, I think, are systems where we think, I think it's just one planet. The red is two planets. So the azimuthal distribution is not significant. It's just they did it decoratively. But the radial is significant, and it's remarkable because if you look, this is Mercury's orbit. Mercury is awfully close to the sun. And nearly all the planets we've discovered in transits, even after you correct for the bias of transit method, which always sees things close, turns out they're very, very close. In fact, this is 10 solar radii, you know, and you can see. So it's, in fact, this paper says, you know, the statistics of extrasolar planetary systems indicate that the default mode of planet formation generates planets with orbital periods shorter than 100 days and masses substantially exceeding that of the Earth. When viewed in this context, the solar system is unusual. Here, the raw contrast to our solar system is striking. So we definitely are seeing from Kepler's results very interesting, wrong computer, very interesting motions. Okay, so these were indirect techniques. Now the talk really begins. So the thing that we're doing, oh, that's fine, I'm doing great. Yeah, thank you. So now, if you actually, what if you really wanted to get light from the planet itself? Up to now, the transit technique was looking at essentially absence of light from the star. The radial velocity was looking at the shift of the light from the star. But what if you wanted to see light from the planet itself? Here's the problem you run into. This is what is called a point spread function. When you point your telescope, let's say here's the Hubble Space Telescope, at a star, and let's say you're looking at a star that's really far away, so you should see, you would expect, a dot in your detector at the end, you know, or in the film, or whatever you have in the back. By the way, at the Hubble Space Telescope, originally they were thinking they were going to put film in there. And then every once in a while the astronauts would take the film home and put it in the room. Yeah, that didn't, I'm glad they didn't do that. So anyway, but instead of seeing a dot, like my red laser pen would show, like it's a dot, you see this blob. This blob is the spreading of this point into this functional form. So it's called the point spread function. It's this point has been spread to this pattern called the Airy pattern. There's a disk, and then there's a ring. There's actually a bunch of rings. We can't see the rest. And if I looked at that from sideways, it would be this shape. This is called the Airy function. So the Airy disk is this part, and this is the first Airy ring. If that is the light that we see, so now imagine we are aliens. We are 10 parsecs away. A parsec is 3 light years, so that's about 30 light years away. We're 30 light years away. We're looking at this solar system, at our solar system. We see our star. We see this light. And then we say, are there any planets? Yes, there's Jupiter right here. Do you see it? No. Okay, let me help you. So what we're going to do is now see the same thing on a logarithmic scale. Logarithmic scale really biases towards letting you see the little stuff at the expense of the big stuff. So here's a logarithmic scale. That's the same curve that we just saw on logarithmic scale. You see all these rings that were not visible before. Here's Jupiter down in an ocean 40,000 times deeper than its own light. In other words, the amount of light that Jupiter is putting out at this point, this far away, is 40,000 times less than that wing of the point spread function. Remember, originally I said Jupiter is 1 billion times dimmer. When I said it's 1 billion times dimmer, I meant like, if I were to put this star about here, that height compared to that height is 1 billion. But when Jupiter's away, you get an advantage from the fact that you're getting away from the peak of the starlight, but it's still 40,000 times deep. Earth is 40 million times, by the way, even at its. So here's the problem. You're trying to see basically a needle in a huge haystack. How can you ever be able to pull out the light from a planet to see this, to pull out of all the light from the star? And that technique is called, really related to the fun event that we had just a few weeks ago, the eclipse. Now you guys remember the eclipse? We have this curious thing that, we have another one of the marvels of our solar system. We have a moon that is 28 arc minutes in diameter, and we have a sun that is 28 arc minutes in diameter. The moon is 400 times smaller than the sun, and it's 400 times closer. Isn't that cute? So that we get these things called perfect eclipses. And that's really remarkable. Well, sometime in the 1930s, Bernard Liot in France tried to see if he could design a telescope gadget with which he could see the corona of the sun, which those of us who were lucky to see the eclipse got to see. And he called it the coronagraph. Okay, and the coronagraph, he invented this, the Liot coronagraph, and the basic thing is that when you look at a telescope, the front of a telescope looks like this. That circle there is because usually telescopes have a secondary mirror, and so that part of the light is blocked. Not a big deal. But when you focus the light, you get that blob. Now he said, why don't I put a little disc to take away the main part of the blob of the sunlight? And then he wanted to see light from around the sun. It turns out when you do that, and you put another lens and you look in this plane, which is what the optics people would call a pupil plane. Now people call it a Liot plane, named after him. There is some funny pattern of light created from the diffraction of starlight that has been messed with like this. And he put a second mask there and he focused it, and he was able to get rid of something like 98, 99% of the starlight. And 98% is great, and with it you can begin to see a lot. But what we want is 10 to the 9th. And so we need more technology. And for that, there's a technique called chronography, and there is a space telescope now called WFIRST that is slated to do this in space. WFIRST has a bit of a history. Some organization that I will not name built a bunch of these telescopes for the US government, and that organization did not want all of their telescopes. So the ones they didn't like, they gave to NASA. You can have this. This one is not good enough for us. So we ended up with 2 of these telescopes. But they're still very fine space telescopes. Each is the size of the Hubble. Their day job, so to speak, is to work on dark energy. And a couple of years ago, or 3 years ago, people said, why don't we build another instrument in there to do a coronagraph in space? And so to see what that does, now it's time for another video. I'm going to just because, no, it's not going to work there. So I'm going to bring it over here. And you're going to see a video, hopefully, right here. Now, if we have audio, that'd be awesome. Thank you. And if you don't, I'll narrate.
We should.
A distant star is orbited by 2 planets. One looks similar to the Earth, the other is a gas giant. When viewed from a distance, the 2 planets disappear into the glare of their sun. How could we ever find these planets all the way from the Earth? By using a space telescope with a coronagraph to separate starlight from planet light. As the star's light passes through the telescope's large mirrors, it picks up small distortions. Diffraction adds concentric rings to the image we see. To reveal the planets First, the chronograph uses a mask to block much of the star's light and redirect the remaining light to the outer edges. A washer-shaped device can now block most of the rest of the star's light. Because the planet's light comes in at an angle, it misses the mask and passes through the center of the washer. But when we turn up the image signal by collecting more light, we can see that the planets are still hidden under blobs of leftover starlight. To remove these blobs, the chronograph has a special deformable mirror that can change shape by using hundreds of tiny pistons. This can correct distortions in the light beam. As the mirror deforms, the blobs of light as seen in the monitor slowly begin disappearing, finally revealing the brighter of the two planets. Afterwards, the fainter planet also comes into view. We can now see objects more than 1 billion times fainter than the star. And if the light from these planets is passed through a prism, we can spread it out into rainbows of color. But some colors are missing. They were absorbed by gases in each planet's atmosphere, giving us important clues about their composition. The search for life in the universe has taken a new step forward.
So that is a promotional video. So the next part of this talk is a little bit more technical, but I'm going to try to kind of not get it too technical. Basically, when you're dealing with coronagraphs and you're trying to ask how good is a coronagraph, one of the main things that people want to know is what the coronagraph contrast is. And the contrast is evaluated by assuming the star is somewhere out in the field where you're going to be looking for planets and seeing how much light do you see, and then you put the star back in there where it's supposed to be hidden, and you see how much light you see in the same spot. And that ratio, which should be like a factor of a billion, which is what we want, is the chronograph contrast. This whole area that we are creating with the deformable mirror to produce this really dark, basically region, dark zone, it's called a dark hole. And the dark hole is the thing that's left over starlight is called speckle. So this is unwanted speckle in the dark hole. All right, so let's use this one. Here's this is the state of the art of coronagraphs right now at this moment. This is a ground-based observatory called the Gemini telescope in the southern hemisphere. It is, there's an instrument in there that was led by a colleague of mine, Bruce McIntosh, who's at Stanford. And what they are doing here is they basically can do a ground-based telescope. They can't go to 1 billion, but the state of the art is 1 million, so 10 to the minus 6. And so with that, you can't see Jupiters, but you can see extraordinary sized planets. So in this case, what they've done is they took an image around this star 51 Eridani, and around 51 Eridani, there's this planet B, and you can just see it sometimes in this area. And what you're seeing from frame to frame is the same image at a different wavelength. And which wavelength? It's basically these wavelengths. And this is a methane feature. This is a methane absorption feature, I think, right here. And what you can see is that at some wavelengths, this thing has a lot of light to give, and in other wavelengths, it doesn't, but it's basically sitting there. And so this is the kind of image you can get by suppressing a ton of starlight. Okay. So what we want to do with this W-first coronagraph now is to go from that level of light that we were just seeing, 6 orders of magnitude, actually 10 minus 6, so about 3 orders of magnitude to the 10 to minus 9 level of contrast. You can see that to see Jupiter, you need that basically this is the dimmest thing our instrument can see in contrast land. And you can see there's the contrast of some planets, here's the contrast of Jupiter, Saturn, and we're kind of getting to the point where we can see Jupiters and Saturns for a certain angular separation. And the future of seeing Earths requires yet further advances. And so another project that I'm working on is for when you guys would be doing this, it'll probably launch in the 2030s or so for seeing Earths. Now a little bit about how you make a space telescope like this. And in this case, this is the W First Space Telescope. This is the primary mirror. That's 2.4 meters. And then in the back is where all the instruments are. Now, these space telescopes typically work like this. There is one main observatory that collects the light. And so it's got a big primary mirror, secondary mirror, and then compressed beam. There's a little pickoff mirror that sends that compressed beam to one client or another client, one instrument to another. So one group has does dark energy, and the other group looks for planets. And you negotiate for time on this instrument. And so so this instrument does multiple things. This part is dark energy. That is the coronagraph, and that's the coronagraph instrument. All right, right. So here's a picture of the actual primary mirror assembly. And this company, Harris, is the company that made these telescopes in the first place. You can see it's basically, the telescope is built, the instruments are being built. This is what the coronagraph instrument will look like in its own cage. These optics are only like yay big, and they're extremely precisely built. And this is a very obvious, I'm sure intuitive to everybody how this works, but basically you're manipulating light. It's actually not so bad. A bunch of these are mirrors, you can just ignore them, they're just bouncing back and forth. But here you're basically focusing the light, you're bringing it back out. These are the deformable mirrors, DM1 and 2. That's where you manipulate the phase of the light so that you can do this trick of optimizing the coronagraph performance. And then after that, basically you have these masks, and this is at the end is where you create the image. Then, in addition to the image, what you can do is, this is the image plane where you would expect to see the star and the planet. What you can do is instead do this trick where basically you expand this light into a spectrum. For every pixel here, you get a spectrum there. So that you can say this part of the picture has this spectrum, that part of the picture has that spectrum, and then you can see where the planet is and look at the spectrum for that part. And you can get a spectrum like this from which you can infer what kind of gases are in the planet. Now, just to explain what is the importance of this, is that planets, understanding what kinds of gases the planets are in the atmospheres of planets, tell us a lot about what the planet formation is what kind of planet formation theories are correct and which ones are not correct. Yeah, there's also another one, which is some old idea by, I think it's Lovelock, in the 1970s, which said that if I look at a planet and I see methane in the atmosphere, and at this, which is it's a very reducing. Now I have chemists to help me, so if I start saying something really wrong, you have to stop it. And then if I see ozone, which is highly oxidizing, these two things will titrate each other out. They will basically get rid of each other. They will combine and rain down or whatever they do, and they won't stay there in equilibrium forever. So if I've got ozone and methane at the same time in a planet, something is generating these. So what could it be? And at the time, the thought was maybe it could be biology that's generating these. So I can infer biology going on the planet far away by seeing these things that normally would not stay at equilibrium. So that's sort of the kind of thing people are looking at when they look for spectra around other planets. Some other details of just our bread and butter. This is how what we spend our days thinking about. For example, if you want to see a planet around another star, if you want to image it, notice how much of the time you cannot image it. If its back is to you, you can't image it, right? If it is inside what is called the inner working angle, where the coronagraph, we just could not suppress the starlight enough inside this area, you can't image it. So in all, maybe a third of the time you can really image it. So knowing the planet's orbit phase is really important for imaging for imaging it. All right, so and this gets maybe I won't tell you too much about this, except it's just to say that when there's an iterative process of sensing the light, sensing the electric field that the light has, and iteratively basically suppressing the light, and you can see, when you first look at a star, it might be that you only are suppressing it down to 10 to minus 4, and you keep iterating, and as you iterate, you get all the way down to like 10 to minus 9 of the planet, of the starlight, at which point the planet will show up. This is a graph that says that for us it matters how many iterations it takes to get down to the lowest contrast, to the best contrast. And what happens is if you don't do a good job, you spend all your time digging the dark hole, and then you lose time. In a typical scenario, when we observe a star, we would first look at a bright star, so we get a lot of photons. Using that, we train our equipment so that we get the dark hole. Then we point at the subject and then take the picture. The picture can take hundreds of hours, actually, to take, because there's, oh, yeah, one thing about these is we get rid of all but 1 in 10 to the 9th of the light of the star. Along the way, we lose also 99% of the planet light. So the planet, the photons from the planet are coming, like if I look at that, which I shouldn't, that's about, million trillion photons per second right now coming to my eye. So it's quite bright. The planet is coming out at 1 milliphoton per second. In other words, every 1,000 seconds a single photon shows up. So it's extremely dim. So here's a picture. This is what I was doing until for 2 or 3 years with my team at JPL, where we were modeling the telescope. One of the things that we want to do is basically, and I didn't mention this in the previous slide, so I'm going to go back. And one of the advantages, basically we look at the other star, we get the speckle pattern, we memorize what that is, we essentially store it. When we come to the star we want to see, we subtract the pattern we saw before, so that we can do a little bit of better subtraction, better rejection of the speckle. Problem is that as you look from one star to another, let's say our sun is over here, heating our right arm here, and I'm looking at this planet, this star, this is my reference star, so I'm getting sort of, and as a result of this heat entering one side, the telescope's going, kind of turning a little bit, kind of being imperfect slightly, like at the micron level, which causes problems. And then when I look at this other star, it actually changes. And so as it changes, these thermal variations, how much do they change the speckle? So we were doing these models where this is, many hours, hundreds, tens of hours in this case, were simulated and fast forward. And our goal was to show the speckles are not moving. Well, they're moving, but they're not moving a lot. And so it turned out that what we showed was that the behavior of the instrument was stable enough that the subtraction could take place. All right, and this is basically, this shows that before you do the subtraction, beta Uma for this particular star is the reference star, the bright reference star. 47 Ursa Major is, Ursa Major, by the way, is the Big Dipper. It's a big bear. So it's 47 Ursa Major is one of the planets around in the Ursa Major constellation. And you can see one of the stars. You can see when you look at it, you don't see the planets. And these are, we had put in, this is a simulation, we put in some planets. And no sign of planets. But when you do the subtraction, it looks a lot better. When you do this technique of angularly decoupling the light, you see the planets show up, basically. And this angular decomposition, decoupling is where if you turn the telescope, your speckles move with your telescope, but the planet doesn't. So the thing that stays the same as you turn it, is the planet. And that's the technique of ADI. Now, another technique that people have proposed is to actually do what the sun does, using what is called a star shape. And the star shape involves basically you take this object and you send it to space a little distance away, like 40 million meters away. And you somehow manage to aim at the star you want with these two things at that distance coordinating each other, so that they're right in the line in the same site. So that's called a star shape. The advantage of the star shape is that the suppression of the starlight occurs right there. This device now doesn't have to do anything fancy. It just needs to be a photon bucket. Just grab all the photons that come and see that. So this can see even at Earth around a sun-like star far away. The disadvantage is this. Suppose you want to go from that star to that star. This thing is 40 million meters away, so suddenly this thing has to take a big space journey to go over in front of you the other direction. and you're going to run out of fuel on whatever propellant you got into in the spacecraft. So the star shade does marvelous things for a short amount of time. The coronagraph does, a little bit less marvelous things for a very long time. So basically, that is the story I was going to tell you. That the project that we're working on, which involves this telescope W-FIRST, that we have finished our technology milestones, and launch is expected in 2020. And I think that the legacy of all of this stuff will be, for those of us who take this view of it, is we're going to find that the universe, much more than anybody ever thought, is a place in which the conditions that we observe in the Earth are very, very special. That just like we saw with the Kepler results and with the radial velocity results, what we'll see when we look for planets around other stars, we will find very interesting things. But my gut feel about this is that we will find that these conditions that we have are going to be very hard to find randomly. Now, let's take another view. We all believe that a God exists. We believe the God of this universe exists. He is sovereign to make planets with life in it in as many places as he chooses. Right? Now, if you've read the C.S. Lewis Space Trilogy, which you should, you remember that he certainly took that view. So it's entirely possible that we will see signs of life if we believe that God created life, which we do. However, here's the way the logic works. If in the laboratory I find that the probability for random production of life is low, and I observe it, I have observed a miracle, in a sense, you see. Another way to put it is that if, as I speak, suddenly somebody just walks through this wall and says, hi. Okay, you go, oh, gee, walking through walls is pretty common, more commonplace than I thought. No, you go, that was totally weird. That is the logic of what I'm talking about. In other words, you already know the probability of somebody walking through this wall. So when you see somebody walking through this wall, you now know what you're dealing with, something very, very unusual. And that, I think, is sort of the logic that we could apply to this. That we would love to see what we see. We may see no life. We may see some life. But we already know that life is very difficult to produce randomly. So I'm going to stop right now and just let you guys ask questions, and then we can go from there.
For questions, I'm going to go ahead and have you talk a little about.
So, given that you're having so few photons come in from something, and it's not like you can just grab a focusing ring and manipulate these pistons on this controllable mirror, how are you optimizing what that mirror actually looks like? It seems like that's an incredibly
beautiful question. That's a really, really good question. I said the theory about good questions. When a speaker says good question, it means I don't know the answer. When they say great question, it means I used to not know the answer, but we figured it out. I'm really happy you asked, so I can brag about how I know. So I'll say great question. So anyway, the answer is, the question that was asked is this. If I'm getting one photon out of this planet every so many thousand seconds, or hundreds of seconds, how in the world did I get enough signal out of which to decide what to do with those particles? And the answer is this, that it's a very technically complex thing to describe. But basically what we do is, number one, let me go to the upshot of it. When we look at the planet, the deformable mirror is frozen in whatever the state we decided is good. So we don't have enough photons to do anything anymore. It's done. At that point, we just hope that it doesn't move. And that's why we did those studies to say, do the thermal properties, is it going to stay stable enough? Because we can't figure out what to do with it. Okay. So that's one part of the answer. But how did we ever get it? And the way you ever get it is from something called the heterodyne gain phenomenon. Light is coherent. When you look at light from a star, you're looking at light from individual atoms on the star. So these photons are coherent. Each one of those photons it was generated by an atom from that star and is coherent with itself. Okay. So what ends up happening is that when when you are first training your instrument, and let's say you're not set up right, so you get actually a bunch of starlight. Okay. Then what you can do is you can on purpose mess up the deformable mirror, so you flood this area with light. It turns out that it takes a bit of math to show this, but the electric field that corresponded to your good situation gets essentially multiplied by the bad situation, and you get this amplification. So you see everything exaggerated, and you go, oh, we get these speckles. Well, I know what makes those speckles when the phase is like this. That comes from having a model of the system. Then based on that, you fix it, you take away the artificial, big lot of light that you have pumped into it, and that's those iterations. So in each iteration, you essentially flood the area with coherent light, you let it mix with the field that was so small, and you see an amplified version of it. Using that, you figure out what to do, you fix it, you don't do such a good job, so you iterate over and over again. But it's like, that is really what, we get paid to do all the time, is to scratch our heads and how to do this. Yeah.
Correct me if I'm wrong, but I saw that through several studies, you could kind of guess what elements and other stuff were in each of the planets. Is it possible that there are elements we haven't yet discovered on our Earth on those planets?
Well, the general, you can call it the cosmological principle, is that there is one universe with one set of laws. And I think we are all in agreement. That's a very good working assumption. So basically, if you go down from the elements, one level down, to the constituent nuclei, and then even from there to the quarks and leptons, the universe has just the same particles here as everywhere else. So there's the proton and the electron, and there's the strong nuclear force and the weak nuclear force, and the electromagnetic force and the gravitational force. And those interactions basically determine what kinds of nuclei are going to be stable, what kinds are not going to be stable, what the electron orbitals are going to be what, all those things, the sp, the ef, all of that stuff. Those are all from the fundamental laws of physics. So unless we think that this part of the universe, just from geometry, somehow the laws of physics are changing, well, maybe we'll find that out, but we certainly don't dare right now assume it because we have no idea what would cause it to change the law. So it's totally assumed that's the same. And I'd say this, that the pattern of spectra that we do see in almost like a fingerprint way, do indicate stuff we see on Earth. They just seem shifted. But except for the shift, the relative spacing totally match, what we expect.
So you said that the light from the planet that you're trying to see, most of it gets blocked. Is there a way of telling the difference between the photons from the star and the photons from the planet? And if so, could you actually get more light reflected off the planet to you to see with?
There are ways the technical word for what you're asking is to decouple the planet light from the starlight. So we want to decouple them. So the starlight has a different spectrum than the planet. So sometimes what you can do is measure the spectrum. But imagine, now you're getting one photon every 1,000 seconds. How many photons do you need to actually get a spectral, spectrum? It's a lot of time. Actually, that's sort of these days my job is I constantly calculate these times every day for people. What about epsilon Eridani B? How many seconds for that? And it's like 200 hours. It's like so. But basically, the answer is it's difficult. In other words, once you have, first of all, the planet has a reflectivity, which we call albedo. It's got an albedo, and that's God-given. So I'm not going to be able to change the planet's albedo. It's just going to be the fraction of light that it's emitting. And that's called the flux ratio. So for every unit of starlight, if I see 10 to the minus 9 units here, that's the flux ratio I can expect from this planet. Given that that's what it is, and I can't change that, the only thing I can do is suppress this. Or what I didn't suppress, at least predict it. So I go and say, well, so if I put my instrument in a very particular mode with a deformable mirror doing exactly its magic, if I can keep everything really still, I can first point my telescope at a different star. It doesn't have this planet. Just see what kind of speckles I see. I say, those are going to be what speckles I expect. I come back, and I just subtract those speckles. That same pattern that I saw there, I just do a minus sign from this minus that. That's my final, best chance of getting rid of the star background. At that point, I really just say, that part looks bright like a planet. So anything there, I'm gonna call plan. I cannot say anything different. So that's sort of it. Okay. Oh,
So I just had a question about the lenses. I know you get distortion from the different wavelengths of light passing through lens materials, and there's also probably some effects of the crystal structure of the materials of your lenses as well. So I was just wondering, is that anything that you have to compensate for using this system?
I think you can compensate and calibrate on the ground, and you expect those properties to stay the same. So you calibrate your spectrometer, then given what you've got, 550 nanometer light falls here, 600 nanometer light falls there. Basically, the orientation of the prism, the lenses, and the focal plane are all now fixed. And so this pixel in the image is going to go through this part of the prism, it's going to fall there. And that's kind of essentially fixed. And so you can just calibrate it on the ground.
So those don't move relative to each other after they've been installed and calibrated?
Right, and if you can do this. You can look at a reference star, like you pick your favorite, Beta Ursa Major. And every so often, you go back to the Beta Ursa Major and you look at that spectrum again. And you say, that didn't change much, therefore things seem to be fine. And, otherwise you have to recalibrate and say things are shifting. 15 minutes till pancakes.
You had mentioned using the L2 location for stationing.
Oh, you saw that. I didn't even mention it.
Oh, I'm sorry. Yeah, you
Yeah.
did mention it. I just saw it. You mentioned also that you had an issue with thermal warping on the actual spacecraft. How far out would you have to actually put such a telescope in order to cut down on having to compensate?
Okay, good question. So the question is, there are different orbits. So if the lowest orbit is low Earth orbit, it's only a few hundred miles up. That's where the space station is. That's where Hubble is. You're getting the sunshine. You're getting Earth shine. And you're getting eclipse, occultation. In other words, you're going, here's this, let's say that's the sun, and I'm the Hubble. So when I go on the backside, suddenly, boom, a kilowatt per square meter goes away. And in fact, at the beginning, the solar panels on the Hubble would just go snap to another mode every time they got hot and cold. They're like the oven, so they had to change those out. It was really a serious problem. The orbit that these things are going to is a different orbit. It's called the second Lagrange point. That's very far distance away from the Earth. The Earth is like essentially, I think it's like an arc second in the sky. It's like non-factor. The problem is the sun itself. If I've got, if I'm looking at if this is my spacecraft, and here's the sun, I look at star A compared to star B, or I have a different role, different parts of the spacecraft actually get hot. Like if I look too far at the bottom, it gets hot. We were doing these exercises about a couple of years ago, and we were having this one situation where as we looked at the star, one other star, suddenly something just changed on the spacecraft completely. And it's all in the model. It's like, what in the world is going on? And what's happening was, there was, the solar panel had a gap between one panel to the other, and normally you would tape that up. In our model, we didn't tape it up. So light was going through the crack, heating up a little piece of metal, which was expanding and curving up here. And it was like, we were seeing in the model, like, what is this? And we found out it's like light going through a crack through between two panels that, was doing it. So then we put a tape in the model. But L2 still has the sun. That's the answer. So that you can't do it.
You just picked L2 because it just stays in the same
Well,
place.
it's first of all, it's very stable orbit, except for the fact that you still have the sun. In many other ways, it's a very good orbit. And Earth is not a problem. Okay?
So as you do this attitude decoupling as you roll,
Yeah.
how significant is the insulation impact are you rolling enough that you're exposing a significantly different portion to the sunlight?
Yeah.
Or is it just, you know, a degree or two of cold?
In my office at JPL, I used to have a rolled up piece of paper and another one taped like this for these kinds of questions. So it turns out if this is, let's say, the solar panel, and the solar panel is actually very big compared to the telescope. So here's, let's say, where the sun is. There is an angle at which I can look at my star. Let's say I just look at that star at an angle such that the vector that goes to the sun and the vector that goes to the star, those would define a plane. The normal to the solar panel, I can put in that same plane. That's a plane of symmetry. I'm only allowed to go 13 degrees this way and that way in this particular instrument because of other reasons. And by being symmetric about that angle, the insolation is the same at both angles. That's a good question. Boy, you guys are really sharp. I don't get questions like this. No. Oh, yeah, one more.
What happens when it appears that two stars, you know, thousands of light years away or something, are very, very close to one another? And so can you block, like, the light from one is just far enough away that it would be interfering?
It's a current headache. So there's a joke. Now, I hope I say this joke correctly. 3/2 of the stars in the sky are binaries. I think that's how the joke goes. Because half the stars in the sky are, half the things you see in the sky are stars that are really binary. So in fact, the number of stars that are out there that correspond to them is 3/2 of. Anyway, so there's a lot of binaries out there. And it turns out a lot of the juiciest targets, the ones that are nearest us where the planet separation shows up the most, are actually binaries. And binaries are a problem because, you know, that other light, like you said, is going to come in. There is, in fact, I mean, this is funny because this is like emails we were exchanging last week. There's a group at NASA Ames who has done some study that was just presented at San Diego Optical Conference last month, that basically they can say, you know, we have all that deformable mirror actuators. We will use half of them. It turns out that the number of little speckles that you can kill off is like a whack-a-mole, you know, is proportional to the number of actuators you have. And so we said, why don't we just save up half of our actuators, and with one half make a half circle that's dark. If we know where the planet is, or we can guess where the planet is, we can make a half circle, use the rest of it to actually basically knock out this part of the leakage of light from that star. So use half our deformable mirror actuators for that star, half of it for this star. And then, you know, get one spot. It's not as big as the original one, but one spot where we are now like shooting with two hands. You know, basically killing off both stars. So that's currently being like modeled and tested, and there's a paper. We haven't tested it in the lab yet, but we'd like to try that. If we can, then suddenly we get a whole lot of nearby stars that are accessible. That's a really great question.
I guess, actually, I just have
Yeah.
one more,
Okay.
I guess, sort of simple question. How big are those actuators? I mean, I would imagine that they're very, very small. You have to have a lot of those, but like, just
Actually, I
for
don't know for sure. I know that the
reference.
deformable mirrors that we have are on 1 millimeter centers. I don't think the actuator is a large fraction of that millimeter, so it's maybe 100, 200 microns, you know, in diameter. So the whole mirror is like that big, and the little actuators are just little. It's a big ceramic thing, and so there's 2 or 3 technologies for doing it. You know, one is just piezo, another one is something else. But yeah, it's state of the art. It's super fancy stuff. Yeah.
So is it possible to build bigger mirrors, maybe in the future?
They are
with
building
more
bigger
actuators?
mirrors, and in fact, the next mission is boasting a much bigger deformable mirror. Huge. I mean, that's huge.
Yeah.
Actually, the Keck telescope, which is 8 meters, is a set of deformable mirrors. So you can get big deformable mirrors, but those are now have actuators this big, and they're only changing things on the scale of this. Whereas what we're doing for this mission is the main telescope, the big light gathering thing, is all fixed. We just correct it after the beam is compressed in this fine, you know, compressed space. And then we need, obviously, the fine structure. Yeah. All right. We don't want to exhaust everybody, maybe. Okay.
Well, maybe that's a good time to close.
Wait.
One last comment here. Since I got the mic. My thought is maybe, what do you think? Should we try to get one more physicist on staff here and go after this guy?
This was a setup.
Let's give her a speaker. Thank you all for coming. There's pancakes apparently going on somewhere, so we'll have time to thank you.
This was quite a valiant effort by our
Yeah.
AV folks too, because